Now in this lecture we'll answer two questions. On both questions we'll find out the area of the shaded region. So we'll start with the first question. In the drawing we have three semicircles. This is the biggest semicircle. It contains those two smaller semicircles. You know that the radius of this semicircle is equal to 2 units, the radius of this semicircle is equal to 1 unit. Again, our task is to find out the size of this shaded area. So first of all, we define the center of this semicircle. This point is point P. We define the center of this small semicircle. This point is point Q. We define the point of tendency of tangent AB with this semicircle. This point is point M. We define the point of tendency of tangent AB with this semicircle. This point is point N. And we will define the center of this biggest semicircle. This point is point O. And we define the radius of this biggest semicircle as X. Can implement rule 1 here. We have the radius PM that equals to 2. The radius PM is drawn to point M, that is the point of tendency of the AB with this semicircle. Whenever your radius is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MP. If AB is perpendicular to MP, it means that this angle equals to 90 degrees. This angle also equals to 90 degrees according to rule 1. Likewise, we have tangent AB is tangent to this circle as point N. The radius Qn is equals to 1. The radius Qn is drawn to point N, that is the point of tendency of tangent AB with this semicircle. Now, your radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NQ. If AB is perpendicular to NQ, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to the sum rule, rule 1. We define the touching point of those two semicircles. This point is point T. So, those two semicircles have an external line between them at point T. This is to say they touch each other externally at point T. And whenever you have an external line between two circles or semicircles, you can implement rule 10. So repeat quickly on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects their centers together passes through their touching point. In the drawing, you have those two circles that touch each other externally at this point, point P. The center of this circle is at point O. The center of this circle is at point M. The straight line that connects the centers together is of course the straight line OM. And according to this rule 10, the straight line OM must pass through point P, that is their touching point. Or the straight line OM must pass through their touching point, that is point P. Or OPM is one straight line. Again, OPM is one straight line according to this rule 10. So if we implement rule 10 in our drawing, we have those two semicircles that touch each other externally at point T. The center of this semicircle is at point P. The center of this small semicircle is at point Q. The straight line that connects the centers together is of course the straight line PQ. And according to rule 10, the straight line PQ must pass through point T, that is their touching point. Or PTQ is one straight line. So we join point P and Q together by straight line, and P the center line PQ must pass through point C. This is your touching point according to rule 10. So you can see from the drawing that indeed the center line PQ passes through point C. That is their touching point, exactly according to rule 10. So in the next step, I'll copy this quadrilateral PQ and M in a new page, but before that, so we just write down that PTQ is one side line, and therefore PQ in total must be equal to PT plus TQ. So PQ equals to PT, PT is the radius of this semicircle, that is 2. Plus TQ, TQ is the radius of this small semicircle, equals to 1. So in total, we actually found out that PQ equals to 2 plus 1, that is 3. So PQ equals to 3 meters in its length. In the next step, I'll copy quadrilateral PQ and M in a new page, and we'll do a construction in the new drawings. So actually, this is quadrilateral PQ and M that I copied from the original drawing. So in the next step, we do a construction, that is to say from point Q, we'll do perpendicular on PM. Again from point Q, we'll do perpendicular on PM. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and PM. This point is point L. When doing this construction, we can do quadrilateral QL, MN. Quadrilateral QL and M, we have 1, 2, 3 angles, and therefore this fourth angle must be equal to 90 degrees in its size, according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore this fourth angle must be equal to 90 degrees in its size. So in quadrilateral LQ and M, we have 4 right angles, and therefore it is left angles. But we also know that the opposite sides of rectangle are equal to each other. So in rectangle LQ and M, side QN must be equal to the opposite side LM, but QN is 1, therefore the opposite side LM must be also equal to 1 unit in its length. So what is the length of the missing line segment PL? PL equals to PM minus LM. PL equals to PM minus LM. So PL in total equals to PM, PM is 2, minus LM, LM is 1. So in total PL equals to 2 minus 1, that is 1. So PL equals to 1 unit in its length. In the next step, we'll implement the Pythagoras theorem. This triangle PLQ. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares of the quadratic glass. So, in the right triangle PLQ, here by PT is information from Pythagoras theorem. So, in the right triangle PLQ, according to the Pythagoras theorem, PQ square, that is the square of the hypotenuse, equals to PL square plus LQ square. PQ is 3, therefore PQ square is 3 squared, that is 9. And it equals to PL square. PL is 1, therefore PL square is 1 square, that is 1. Plus LQ square. LQ is the missing side, so leave it as it is. And total, if you found out that 9 equals to 1 plus LQ square, here subtract 1 from this equation. And finding that 9 minus 1 is 8 equals to LQ square. 8 equals to LQ square. Here you take out of this equation. And finding that LQ equals to the square root of 8. Here substitute 8 by 4 times 2. So the square root of 4 is 2, so inside the root we'll have to leave 2. So in total we should know that LQ equals to 2 times root of 2 units in its length. LQ equals to 2 times root of 2 units in its length. So in order LQ and M, the opposite sides are equal to each other. So side LQ equals to the opposite side MN, but LQ is 2 times root of 2, therefore MN must be equal to 2 times root of 2 units in its length. So this is line segment MN is equals to 2 times root of 2 units in its length. The next step, we find the length of line segment MOSA. So what is the length of the missing line segment ON? ON equals to MN minus MO. Write it down. ON equals to MN minus MO. So total ON equals to MN. MN is 2 times root of 2 minus MO. MO is 8. So in total, we found out that ON equals to 2 times root of 2 minus units in its length. Then we say line segment OM is equals to 2 times root of 2 minus units in its length. Point O is the center of the biggest semicircle. So in the next step, we will join points O and Q together by a straight line. Line segment OQ bisects chord EF. Why? Because point Q is the center of this semicircle. Q is the radius of this semicircle, that is 1. Likewise, QF is also the radius of this semicircle, that is 1. In total, EF is the diameter of this semicircle, that is 2, and line segment OQ bisect chord EF into 2 halves. Each half equals to 1. So, line segment OQ starts from the center of this big semicircle and ends at point Q. So, we have a line segment that is one from the center of this big semicircle and bisect chord EF. And therefore, according to all 30, line segment OQ will be also perpendicular to chord EF. That is to say, this angle equals to 90 degrees and this angle also equals to 90 degrees according to all 30. So, pinch me from all 30. According to all 30, a line segment that is one from the center of the circle and bisect the chord will be also perpendicular to that chord. In the moment we have a circle, this is point O, that is the center of the circle. Line segment OM bisects chord AB. Again, line segment OM bisects chord AB according to our construction. And because of the fact that OM bisects chord AB, OM will be also perpendicular to AB. If OM is perpendicular to AB, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to this rule, all 30. So I can implement all 30 in our drawing. What happens in our drawing? From the center of this biggest semicircle, that is to say from point O, we have line segment OQ that bisects chord EF, and therefore line segment OQ must be also perpendicular to chord EF. If OQ is perpendicular to EF, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to all 30. In the next step, we join points O and D together by side line. Point O is the center of this biggest circle. Point is the point of the biggest circle itself, therefore OE is the radius of the biggest semicircle, is equals to x according to our definition. So OE is the hypotenuse of the triangle EQO equals to x. So in the next step, we will implement the Pythagoras theorem on this right triangle EQO. Right triangle EQO. So in the right triangle EQO, according to the Pythagoras theorem, EO squared, that is the square of the hypotenuse, equals to EQ squared plus QO squared. And again, in this case, I triangle EQO, according to the Pythagoras theorem, EQ squared, that is the square of the EO squared, that is the square of the hypotenuse, equals to EQ squared plus QO squared. EQ is x, therefore EQ squared is x squared. And it is equals to EQ squared. EQ is 1, therefore EQ squared is 1 squared, that is 1. Plus QO squared. QO is one side of this right hand triangle EQO, but QO is also the hypotenuse of this triangle O and Q. And again, QO is the hypotenuse of this right pink triangle, triangle O and Q. So we implement the Pythagoras theorem on this right pink triangle Q and O, and we get that QO squared, that is the square of the hypotenuse, is equal to qn square plus no square. Again, qo square equals to qn square plus no square. So x squared equals to 1 plus qn squared. Qn equals to 1, therefore qn squared equals to 1 squared, that is 1, plus no squared. No equals to 2 times square root of 2 minus 8, therefore no squared equals to 2 times square root of 2 minus 8 squared. In total, according to equation 1, if we found out that x squared equals to 1 plus 2 times square root of 2 minus 8 squared. So x squared equals to 1 plus 1 is 2. Here we'll open the brackets of this expression. 2 times square root of 2 minus 8 squared equals to 2 times square root of 2 squared, that is 8, plus 8 squared, minus 2 times square root of 2 times 8. So in total, we found out that according to equation 1, x squared equals to 2 plus 8 is 10, here, plus 8 squared, minus 2 times, minus 2 times 2 is minus 4, so in total this expression equals to minus 4 times square root of 2 times 8. In total, we found out that according to equation 1, x squared equals to 10 plus 8 squared minus 4 times square root of 2 times 8. This is according to equation 1. In the next step, we repeat on the same process that we did in this side of this big semicircle, on this side of this big semicircle. That is to say, we join points O and P together by a straight line. Point O is the center of this bigger semicircle. Point P is the center of this semicircle. So PC is the radius of this semicircle, that is 2. PD is also the radius of this semicircle, it equals to 2. So in total, the diameter CD equals to 4. So at point P, the diameter CD is been bisected into 2 halves. Each half equals to 2. So in total, we found out that from the center of this big semicircle, that is to say from point O, we have line segment OP that bisects chord CD. And therefore, according to rule 30, line segment OP must be also perpendicular to chord CD. If OP is perpendicular to CD, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 30. In the next step, we join points O and C together by a straight line. And we implement the so point O is the center of this biggest semicircle, point C is the point of the biggest semicircle itself, therefore also is the radius of this biggest semicircle, equals to x. So in the next step, we implement the bottommost theorem on this advance CPO. Here by PT is the duration for Pythagoras theorem. This right triangle CPO, CO squared, that is the square of the hypotenuse, equals to CP squared plus PO squared. And again, this right triangle CPO according to the Pythagoras theorem. CO squared, that is the square of the hypotenuse, equals to CP squared plus PQ squared. Essentially, CO squared equals to CP squared plus PO squared. CO is x, therefore CO squared is x squared. And it equals to CP squared. CP is 2, therefore CP squared is 2 squared, it is 4. Plus PC squared, plus PO squared. PO is one side of this green right triangle, but PO is also the hypotenuse of this right pink triangle PMO. So we implement the Pythagoras theorem on this right pink triangle PMO according to the Pythagoras theorem. We get that PO squared, that is the square of the hypotenuse, equals to PM squared plus MO squared. And again, if we found out that PO squared equals to PM squared plus MO squared. So in total, x squared equals to 4 plus PM squared. PM is 2, therefore PM squared is 2 squared, that is 4, plus MO squared. MO is 8, therefore MO squared is 8 squared. So in total, according to equation 2, we can find out that x squared equals to 4 plus 8 squared. So x squared equals to 4 plus 4, that is 8, plus 8 squared. This is according to equation 2. According to equation 1, we already found out that x squared equals to 10 plus 8 squared was 4 times square root of 2 times 8. So we have two questions for x squared. Therefore, we get equation 3 that says that x squared according to equation 1 will be equal to x squared according to equation 2. So x squared according to equation 1 equals to 10 plus 8 squared minus 4 times square root of 2 times 8, and it must be equal to x squared according to equation 2. X squared according to equation 2 equals to 8 plus 8 squared. So in total according to equation 3, we found out that 10 plus 8 squared was 4 times square root of 2 times 8 equals to 8 plus 8 squared. We have 8 squared on both sides of this equation, so 8 squared gets cancelled. Here we subtract 8 from this equation, and finding that according to equation 3, 10 minus 8 is 2, minus 4 times square root of 2 times 8 equals to 8 minus 8 is 0, so equals to 0. So here we let 4 times square root of 2 times 8 of the equation, and get that according to equation 3, 2 equals to 4 times square root of 2 times a. Here we divide this equation 3 by 2, and finally get that according to equation 3, 2 over 2 is 1, and it equals to 4 over 2 is 2, so total this expression equals to 2 times square root of 2 times a. So 1 equals to 2 times square root of 2 times a. Here we divide this equation 3 by 2 times square root of 2, and finally get that according to equation 3, a equals to 1 over 2 times square root of 2. Again, a equals to 1 over 2 times square root of 2. According to equation 2, we already found out that x squared equals to 8 plus a squared. So x squared equals to 8 plus a squared. A is 1 over 2 times square root of 2, and therefore a squared must be equal to 1 over 2 times square root of 2 squared, that is 8. So in total, we should find out that according to equation 2, x squared equals to 8 plus 1/8. So x squared equals to 1/8. Here we multiply 8 by 8 and then divide it by 8 in order to have a common factor with this number. We get that 8 times 8 is 64. And today we should find out that 61 plus 64 plus 1 is 65 over 8. So x squared equals to 65 over 8. Our task is to find out the size of this shaded area. For the drawing, it is very easy to see that the area of the shaded region, it is equal to the area of the biggest semicircle, also the area of those two circles. If we remove from the biggest semicircle, those two semicircles, we will get exactly this shaded region. So, write it down. If you found out that the area of this shaded region total is equals to the area of the biggest semicircle minus the area of the right semicircle minus the area of the left semicircle. So what is the area of the biggest semicircle? We know that the radius of this biggest semicircle is x, and therefore the area must be equal to pi x squared over 2. The area of the biggest semicircle is equal to pi x squared over 2. Minus the area of the right semicircle this is the right semicircle. The radius of this right semicircle is 1, and therefore the area of this right semicircle must be equal to pi 1 square over 2. Pi times 1 square over 2. minus the area of the left semicircle. The radius of this left semicircle is 2. Therefore, the area of this left semicircle must be equal to pi 2 square over 2. So in total, we found out that the area of the shaded region equals to pi x square over 2 minus pi 1 square over 2 minus pi 2 square over 2. So here we take pi over 2 as a common factor out of those three expressions. So inside the brackets we left only with x square over 2 minus 1 square is minus 1 minus 2 square is minus 4. So pi over 2, we have x square over 2, actually, 2 pi over 2 is a common factor, the left is x square. X square is 65 over 8, minus 1 minus 4 is minus 5. So today we found out that the area of the shaded region equals to pi over 2 times 65 over 8 minus 5. So here we will multiply minus 5 by 8 and then we divide it by 8 in order to have a common factor with this number and get that pi over 2 times 65 over 8, and we have minus 5 times 8 is minus 40 divided by 8. 65 minus 20 is 25 over 8 times pi over 2. In the numerator we have 25 pi, in the numerator we have 2 times 8, it is 16. So in total, we actually found out that the area of the shaded region is equal to either 25 pi or 16 exponents inside. So in terms of numbers, it is equal to 4.908 exponents inside. And again, we actually found out that the area that we are looking for in this question, that is the area of this shaded region. In total, it is equal to either 25 pi over 16 square units in size, or in terms of numbers, it is equal to 4.908 square units in size. So we finish with the first question, and the next step I present you the second question. So the second question of this lecture. Our task in the second question is to find out the size of this shaded region. The shaded region is actually this small semicircle, so we have to find out the area of this small semicircle. This is actually the shaded area. So in the drawing we have those two semicircles that intersect with each other. AB is the diameter of this big semicircle. AM equals to 3, MN equals to 3, and NB equals to 2. So in total, AB in total equals to 3 plus 3 plus 2, that is 8. The diameter AB of the big semicircle equals to 3 plus 3 plus 2, that is 8. AB equals to 8. We define the radius of this big semicircle as R, so the radius R must be equal to the diameter AB over 2. That is 8 over 2, that is 4. So the radius of this big semicircle, the radius R equals to 4 units in its length. In the next step, we define the center of this big semicircle, this point is point O, and when you find the center of this small semicircle, this point is point S. What is the length of this line segment? MO. Or OM equals to OA minus MA. Again, this line segment OM equals to OA minus MA. So OM equals to OA. OA is the radius of this semicircle, equals to 4 minus AM. AM equals to 3. So in total, OM equals to 4 minus 3, this is 1. So OM equals to 1 unit in its length. In the next step, we will do a construction, that is to say from this point S, that is the center of this small semicircle, we will go perpendicular on chord MN. Again, from point S, we will go perpendicular on chord MN. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. When we find the touching point of the perpendicular from point S and this chord MN, ST. When we find the length of ST is H. So from the center of this small semicircle, that is to say point S, we have perpendicular ST on chord MN. And whenever you have a perpendicular from the center of the circle towards any chord, it will bisect the chord. According to rule 15. Rule 15. According to rule 15, a perpendicular from the center of a circle towards any chord bisect the chord. And then in a circle, this is point S, this is the center of the circle. This is perpendicular ST, this is perpendicular on chord MN. And whenever you have a perpendicular that is drawn from the center of the circle towards any chord, it will bisect the chord. So perpendicular ST bisects chord MN. If ST bisects MN, it means that MT equals to TN and each half must be equal to MN over 2. So we can implement rule 15 in our drawing. In our drawing, we have from the center of this small semicircle, that is to say from point S, we have perpendicular ST on chord MN. And therefore, according to rule 15, perpendicular ST also bisects chord MN. If ST bisects MN, it means that the first half of MN is MT, and is equal to the second half, that is TN, and each half must be equal to MN over 2 because MN has been bisected. So, according to rule 15, perpendicular ST bisects chord MN. Perpendicular ST bisects chord MN. So, the first half MT is equal to the second half TN, and each half equals to MN over 2. And again, according to rule 15, perpendicular ST bisects chord MN, that is to say the first half MT must be equal to the second half TN, and each half must be equal to MN over 2. MN is 3, so MN over 2 is 3 over 2, that is 1.5. So in total, we found out that MT equals to TN equals to 1.5. This is line segment MT, this is equals to 1.5 units in its length. And this is line segment TN, this also equals to 1.5 units in its length. What is the length of this short line segment? Line segment OT. the drawing it is very easy to see that OT equals to MT minus MO. So OT in total equals to MT, that is 1.5, minus MO, that is 1. So in total OT equals to 1.5 minus 1, that is 1 half. MT equals to 1 half. OT equals to 1 half units in itself. This is the short line of OT, this is equals to 1 half units in its length. In the next step, we'll join points O and S together by straight line. From the center of this big semicircle, that is to say point O, we have line segment OS that bisects called PQ. Why OS bisects PQ? Because PQ is the diameter of this semicircle. So the first half PS is the radius of the semicircle. This is equals to X according to our definition. The second half is SQ, that is also the radius of this small semicircle, that is equals to X according to our definition. So from the center of this big semicircle, that is to say point O, we have line segment OS that bisects chord PQ. Again, line segment OS bisects chord PQ. The first half of PQ is PS equals to X, and the second half is SQ, that is also equals to X. And because of the fact that from the center of this big semicircle, line segment OS bisects chord PQ, line segment OS must be also perpendicular to PQ. If OS is perpendicular to PQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to all 30. According to all 30. All 30. According to all 30, a line segment that is drawn from the center of the circle and bisects the chord will be also perpendicular to that chord. In the drawing of a circle, this is point O, that is the center of this circle. We have line segment OM that bisects chord AB. That is to say, AM equals to MB equals to AB over 2. Therefore, line segment OM will be also perpendicular to AB. If OM is perpendicular to AB, it means that this angle equals to 90 degrees and this angle equals to 90 degrees according to this rule, all 30. So as mentioned before, we can implement all 30 in our drawing. We put in our drawing. From the center of this big semicircle, that is to say from point O, we have line segment OS that bisects chord QP. And therefore, line segment OS must be perpendicular to PQ. If OS is perpendicular to PQ, it means this angle equals to 90 degrees and this angle equals to 90 degrees according to all 30. So in the next step, we'll implement the Pythagoras theorem. We'll define the length of line segment SO is Y. And we'll implement the Pythagoras theorem on this small line triangle SOT. So copy the line triangle SOT in a new page, and we will implement on it the Pythagoras theorem. Here by PT is the evaluation of Pythagoras theorem. Actually, this is right angle SOT, that the curve to the original knowing. In this right angle SOT, SO squared, that is the square of the hypotenuse, equals to ST squared plus TO squared. So write it down. This will be equation 1, so let's only to equation 1. OS squared, that is the square of the hypotenuse, equals to ST squared plus OT squared. OS is y, therefore OS squared is y squared, and it equals to ST squared. ST is x, therefore ST squared is x squared, plus OT squared. OT is 1/2, therefore OT squared is 1/2 squared, that is 1/4. So in total, according to equation 1, we shall find out that y squared equals to h squared plus 1/4. In the next step, we join points S and N together by straight line. We join points S and N together, the right triangle, NSO, and TSN. This is the right triangle, STN. Point S is the center of this small semicircle. Point N is a point on the small semicircle itself. Therefore, SN is the radius of this small semicircle. It's equals to X. So in the next step, I'll copy the right triangle STN and in operation, we'll implement on it the Pythagoras theorem. So here this is the right triangle STN, that is according to the original drawing. This right triangle STN, according to the Pythagoras theorem, Sn squared, that is the square of the hypotenuse, equals to St squared plus Tn squared. Sn is x, therefore Sn squared is x squared, and it equals to St squared. St is h, therefore St squared is h squared, plus Tn squared. Tn is 3/4, Tn is 3/2, therefore Tn squared is 3/2 squared, that is 9/4. So in total, according to equation 2, we should find out that x squared equals to h squared plus 9/4. This is according to equation 2. According to equation 1, we only found out that y squared equals to h squared plus 1/4. We have those two equations, 2 and 1, so we subtract those two equations and get that x squared minus y squared equals to h squared plus 9 quarters minus 8 square plus 1 quarter. So x square minus y square equals to 8 square plus 9 quarters. We'll open the brackets here. We get that it will be equal to minus 8 square minus 1 quarter. So in total, we now know that x square minus y square equals to 8 square minus 8 square is 0. 9 quarters minus 1 quarter is 8 quarters. 8 quarters is 2. So in total, according to equation 3, we now know that x square minus y square equals to 2. The next step, we join points O and P together by straight line. Point O is the center of this big semicircle, point P is the point of the big semicircle itself, and 4P is the radius of this big semicircle. That equals to 4 according to what we have already found out. So in the next step, I'll copy the right triangle OSP in a new equation. We will implement on it the Pythagoras theorem. Here by PT is the abbreviation for Pythagoras theorem. So here, this is the right triangle PSO, that is covered from the original drawing. This right triangle PSO according to the Pythagoras theorem. We get that PO square, that is the square of the hypotenuse, equals to PS square plus SO square. PO is 4, therefore PO square is 4 square, that is 16, and it equals to PS square. PS is x, therefore PS square is x square, plus SO square. SO is y, therefore SO square is y square. So in total, according to equation 4, we found out that x square plus y square equals to 16. This is according to equation 4, while according to equation 3, we already found out that x square plus y square equals to 2. So here we let equation 4 to equation 3. I get that x square plus x square is 2x square. Y square minus y square is 0. And it equals to 16 plus 2, that is 18. So in total, we found out that 2x square equals to 18. Here we divide this equation by 2 and find that according to equation 5, x square equals to 18 over 2 is 9, so x square equals to 9. Our task is to find out this shaded area. The shaded area is actually the area of the small semicircle, this small semicircle. The radius of this small semicircle is x, and therefore the area of this small semicircle is actually the shaded area. will be equal to pi x squared over 2. So this pi over 2 times x squared. X squared is 9, so x squared by 9. And the shaded area equals to 9 pi over 2. 9 over 2 is 4.5. So total this expression equals to 4.5. 4.5 is actually 14.137 square units. So I should hold on that the size of this shaded area it is equals to either 4.5 pi square units in size, or in terms of numbers, the size of this shaded area equals to 14.137 square units in size. So we'll finish with the second question. In the next step, I'll start the lecture. So we'll start with the repetition of the solution of the first question. In the first question, our task is to find out the size of this shaded region. So in the moment we have 3 semicircles. This is the biggest semicircle that contains those 2 smaller semicircles. The radius of this small circle is equals to 2. The radius of this small semicircle equals to 1. Again, our task is to find out the size of this shaded area. So first of all, we defined the center of this semicircle, this point is point P. We define the center of this small semicircle, this point is point Q. We define the point of tendency of tangent AB with this semicircle, this point is point M. Likewise, we define the point of tendency of tangent AB with this semicircle, this point is point N. We define the center of this biggest semicircle, this point is point O. Likewise, we define the radius of this biggest semicircle is X. So here we can implement rule 1 because we have the radius PM that is equals to 2. The radius PM is drawn to point M, that is the point of tendency of tangent AB with this semicircle. And whenever your radius is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MP. If AB is perpendicular to MP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to rule 1. Likewise, we have the radius Qn is equals to 1. The radius Qn of this small semicircle is drawn to point N, that is the point of tendency of tangent AB with this semicircle. And whenever your radius is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NQ. If AB is perpendicular to NQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to the sum rule, rule 1. Those 2 semicircles touch each other externally at point T. So they have external between them at point T. Whenever we have an external between 2 circles or semicircles, we can implement rule 2, or rule 10. So we quickly on rule 10, according to rule 10, the 2 circles touch each other externally, then the side line that connects the circles together passes through their touching point. So we have those 2 circles that touch each other externally at point P. The center of this circle is at point O. The center of this circle is at point M. The side line that connects the circles together is of course the side line OM. This side line OM must pass from point P, that is the touching point. Of the side line OM must pass through the touching point, that is point P, or OPM is one side line. Again, according to this rule 10, OPM is one side line. So we can implement rule 10 in our drawing. Likewise, in our drawing, we have an external between those 2 circles at point T. The center of this semicircle is at point P. The center of this one semicircle is at point Q. And the side line that connects the circles together is of course the side line PQ. And this side line PQ must pass through point T, that is the touching point according to rule 10. So PTQ is one side line. If PTQ is one side line according to rule 10, it means that PQ in total must be equal to PT plus TQ. PT is the radius of this semicircle is equals to 2, and TQ is the radius of this small semicircle is equals to 1. So in total, PQ equals to 2 plus 1, that is 3. PQ equals to 3 in its length. The next step, I copied this quadrangular PQ and M in a new page, and we did the construction in the new drawing. This is quadrangular PQ and M that I copied from the original drawing. So, in the next step, we did the construction, that is to say from point Q, we go perpendicular on PM. Again, from point Q, we go perpendicular on PM. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the construction. We define the touching point of the perpendicular from point Q and PM. This point is point M. By doing this construction, we can do quadrangular in Q and M. In quadrangular in Q and M, we have 1, 2, 3 rectangles, and therefore this 4 points angle must be equal to 90 degrees in its size. According to the rule that the sum of the angles in any quadrangular is equal to 360 degrees. And therefore this 4 points angle must be equal to 90 degrees in its size. So in quadrangular in Q and M, we have 4 rectangles, and therefore it is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle in Q and M, side QN must be equal to the opposite side LM. But QN is 1, therefore the opposite side LM must be equal to 1 unit in its length. What is the ref of this missing nice one? PL equals to PM minus LM. So PL equals to PM minus LM. So PL equals to PM, that is 2, minus LM, that is 1. So in total, PL equals to 2 minus 1, that is 1. In the next step, we implemented the Pythagoras theorem on this triangle PLQ. According to the Pythagoras theorem, in the right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the right triangle PLQ, PQ squared, that is the square of the hypotenuse, equals to PL squared plus LQ squared. PQ is 3, therefore PQ squared is 3 squared, that is 9. It is equals to PL squared. PL is 1, therefore PL squared is 1 squared, that is 1. Plus LQ squared. LQ is the missing side, so we leave it as it is. So in total, we should find out that 9 equals to 1 plus LQ squared. If subtract the 1 from this equation, if I found out that 9 minus 1 is 8 equals to LQ squared. So LQ squared equals to 8. Here we took out all of this equation. If I found out that LQ equals to the square root of 8. Here we substitute 8 by 4 times 2. So in total, we found out that LQ equals to the square root of 4 times 2. The square root of 2 is 2, so inside the root we'll have to leave 2. So in total, we found out that LQ equals to 2 times square root of 2 units in its length. The opposite sides of rectangle LQ and M are equal to each other. So LQ equals to MN, but LQ is 2 times 2, 2 times square root of 2, therefore MN must be equal to 2 times square root of 2 units in its length. This is line 7 MN, that equals to 2 times square root of 2 units in its length. In the next step, define this short line 7 MO as A, and therefore ON must be equal to MN minus MO. And ON equals to MN minus MO. So ON equals to MN, that is 2 times square root of 2, minus MO, that is A. So in total, ON equals to 2 times square root of 2 minus A. So in the next step, we join points O and Q together by straight line. Point O is the center of this bigger semicircle. Point Q is the center of this small semicircle. Chord DF is being bisected at point Q. Point Q is the center of this small semicircle, so the first half QF equals to the second half QE, and each half equals to 1. And because of the fact that from the center of this bigger semicircle, that is to say from point O, we have line segment OQ that bisects chord EF, line segment OQ must be also perpendicular to EF. If OQ is perpendicular to EF, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to Rule 30. So the next step, we join points O and E together by straight line. OE is the radius of the bigger semicircle that is equals to X. So in the next step, we implemented the Pythagoras theorem on this straight line EOQ. This straight line EOQ, EO squared, that is the square of the hypotenuse, equals to EQ squared plus QO squared. Repeat again, in this right hand triangle EQO, EQ squared equals EO squared equals to EQ squared plus OQ squared. EO is X, therefore EQ squared is X squared, and it is equals to EQ squared. EQ is 1, therefore EQ squared is 1 squared, that is 1, plus OQ squared. OQ is one side of this green right triangle, but OQ is also the hypotenuse of this pink triangle. Therefore, according to the Pythagoras theorem, if we implement the Pythagoras theorem on this pink triangle OQN, we get that QO squared equals to QN squared plus NO squared. So today we found out that QO squared equals to QN squared plus NO squared. EO is x, therefore AO square is x squared. EQ is 1, therefore EQ square is 1 squared, that is 1. So in total x squared equals to 1 plus NQ squared plus NO squared. Qn is 1, therefore Qn square is 1 squared plus NO square. NO is 2 times square root of 2, 1 squared, therefore NO square is 2 times square root of 2, 1 squared square. So in total, let's say how know that x squared equals to 1 plus 1 plus 2 times square root of 2 minus a squared. So x squared equals to 1 plus 1, this is 2. And here 2 times square root of 2 minus a squared. Open the brackets of this expression and we found out okay, that 2 times square root of 2 times a squared equals to 2 times square root of 2 squared, that is 8 plus a squared minus 2 times square root of 2 times a. So in total x squared equals to 2 plus 8 is 10. Plus a square, and you have minus 2 times 2 is minus 4, so in total this expression equals to minus 4 times square root of 2 times 8. So in total, according to equation 1, we have found out that x squared equals to 10 plus a square minus 4 times square root of 2 times 8. In the next step, we did the same process that we did on this half of this biggest semicircle, on this and the other half, this biggest semicircle. This is to say we join points O and P together by side 9. Point O is the center of this biggest semicircle. Point P is the midpoint of CD. And because of the fact that line segment OP by set code CD, according to Rule 30, line segment OP will be also perpendicular to CD. If OP is perpendicular to CD, it means this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to Rule 30. Okay, again, because of the fact that line segment OP by set code CD, line segment OP will be perpendicular to CD. If OP is perpendicular to CD, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to Rule 30. In the next step, we join points O and C together by side line. OC is the radius of this biggest semicircle, is equals to x. So in the next step, we implemented the Pythagoras theorem on this right triangle CPO. According to the Pythagoras theorem, in the triangle CPO, CO squared is the square of the hypotenuse equals to CP squared plus PO squared. Okay, again, in this right triangle CPO, according to the Pythagoras theorem, CO squared is the square of the hypotenuse equals to CP squared plus PO squared. CO is x, therefore CO squared is x squared, and it equals to CP squared. CP is 2, therefore CP squared is 2 squared, that is 4. Plus PO squared. PO is one side of this right triangle CPO, but PO is also the hypotenuse of this pink triangle PMO. Therefore, according to the Pythagoras theorem, if we implement the Pythagoras theorem in this right triangle PMO, we get that PO squared equals to PM squared plus MO squared. Again, PO squared equals to PM squared plus MO squared. CO is x, therefore CO squared is x squared. CP is 2, therefore CP squared is 2 squared, that is 4. So in total, if we found out that x squared equals to 4 plus PM squared plus MO squared. So we have PM squared. PM is 2, therefore PM squared is 2 squared, that is 4 plus MO squared. MO is 8, therefore MO squared is a squared. So in total, we should found out that x squared equals to 4 plus a squared. So x squared equals to 4 plus 4, that is 8 plus a squared. So according to equation 2, we found out that x squared equals to 8 plus a squared, while according to equation 1, we only found out that x squared equals to 10 plus a squared minus 4 times square root of 2 times a. So we have two different equations for x squared. Therefore, we can have equation 3 that states that x squared according to equation 1 must be equal to x squared according to equation 2. X squared according to equation 1 equals to 10 plus a squared minus 4 times square root of a. 10 plus a squared minus 4 times square root of 2 times a. It must be equal to x squared according to equation 2, that equals to 8 plus a squared. So we have a squared on both sides of this equation, so a squared will get cancelled. In the next step, substitute 8 for this equation. So 10 minus 8 is 2, minus 4 times square root of 2 times a. 8 minus 8 is 0. So in total, we should find out that according to equation 3, 2 minus 4 times square root of 2 times a equals to 0. Here we added 4 times square root of 2 times a to this equation, and we found out that 2 equals to 4 times square root of 2 times a. Here we divided this equation by equation 3 by 2, and we found out that 2 over 2 is 1, and it equals to 4 times square root of 2 times a over 2 is 2 times square root of 2 times a. So in total, we found out that 1 equals to 2 times square root of 2 times a. Here we divided this equation equation 3 by 2 times root of 2 and find that a equals to 1 over 2 times root of 2. According to equation 2, x squared equals to 8 plus a squared. So x squared equals to 8 plus a squared. A is 1 over 2 times root of 2, therefore a squared must be equal to 1 over 2 times root of 2 squared, that is 8. So total x squared equals to 8 plus 1/8. So x squared equals to 1/8, and we multiply 8 by 8 and then we divide it by 8 in order to come factor with this number. So 8 times 8 is 64 plus 1 over 8. 64 plus 1 is 65 over 8. So in total x squared equals to 65 over 8. Our task is to find out the size of this shaded region. What is the size of this shaded region? From the drawing, it is easy to see that the size of this shaded region is equal to the area of this biggest semicircle minus the area of this left semicircle minus the area of this right semicircle. Okay, repeat again. The size of this shaded region equals to the area of the biggest semicircle minus the area of this left semicircle minus the area of this right semicircle. So the size of the shaded region equals to the area of the biggest semicircle minus the area of the right semicircle minus the area of the left semicircle. The radius of the biggest semicircle is x, and therefore the area must be equal to pi x over 2 minus the area of the right semicircle. The radius of the right semicircle is 1, therefore the area must be equal to pi 1 square over 2 minus the area of the left semicircle. The area of the left semicircle, the radius of the left semicircle is 2, therefore the area of the left semicircle must be equal to pi 2 square over 2. So we have here, we took pi over 2 as a common factor out of those three expressions. So inside the brackets we left only with x squared minus 1 minus 4. X squared is 65 over 8, and minus 1 minus 4 is minus 5. So we multiplied minus 5 by 8 and then we divided by 8 in order to overcome factor with this number. And we found out that in total pi over square times 65 over 8, and we have minus 5 times 8 is minus 40 over 8. 65 minus 40 is 25 times pi over 2 times 8. So it is 25, and over 2 times 8 is 16. So in total we found out that the area of this shaded region equals to either 25 pi over 16 square units in size. So in terms of numbers, the area of this shaded region equals to 4.908 square units in size. Repeat again, the area of this shaded region is equals to either 25 pi over 16 square units in size. So in terms of numbers, it is equals to 4.908 square units in size. So we finished to answer the first question. The next step, a bit on the solution of the second question. On the second question, our task was to find out the size of this shaded area, the size of this small semicircle. So in the drawing we have two semicircles that intersect with each other. This is line 70mm, this is equals to 4 units in itself. This is line 70mm, this is also equals to 4 units in itself. This is line 70mm, this is equal to 2 units in its length. So in total, AB is the diameter of the big semicircle. AB in total equals to 3 plus 2, that is 8. Again, AB in total equals to 3 plus 2, that is 8. The diameter AB of this big semicircle is 8. Therefore, the radius must be equal to half of it. So the radius of the big semicircle equals to the diameter AB over 2. That is to say it is 8 over 2, that is 4. So the radius of this big semicircle equals to 4 units in its length. We define the center of this big semicircle, this point is point O. We define the center of this small semicircle, this point is point S. So AO is the radius of this big semicircle, that is 4. AM equals to 3. So MO equals to AO minus AM. Again, the missing line 7 OM equals to OA minus MA. So OM in total equals to OA, that is 4, minus MA, that is 3. So in total, OM equals to 4 minus 3, that is 1. In the next step, we did a construction, that is to say, from point S, that is the center of this small semicircle, we do perpendicular ST on chord MN. Again, from point S, we do perpendicular ST on chord MN. Whenever you draw a perpendicular from the center of the circle towards any chord, it will bisect the chord. Therefore, perpendicular ST that is drawn from the center of this small semicircle, perpendicular ST bisects chord MN. If perpendicular ST bisects chord MN, it means that MT equals to TN and each of equals to MN over 2. And again, perpendicular ST bisect chord MN. That is to say, the first half MT must be equal to the second half TN, and each half must be equal to MN over 2 because MN is being bisected. MN is 3, so therefore MN over 2 is 3 over 2, that is 1.5. So in total, we should find out that MT equals to TN equals to 1.5. This is the first half MT, that is equals to 1.5. The second half of MN is TN, that is also equals to 1.5 units in its length. What is the length of this short line segment OT? OT equals to MT minus MO. So OT equals to MT minus MO. So OT equals to MT. MT is 1.5 and MO is 1. So in total, OT equals to 1.5 minus 1, that is 1 half. So OT equals to 1 half units in its length. In the next step, we join points O and S together by a straight line. Point O is the center of this big semicircle. Point S is the center of this small semicircle. So line segment OS bisects chord QP because SX, S the first half SP, is the radius of this small semicircle equals to the second half SQ. This is also the radius of the small semicircle. So OS bisects chord QP. And because of the fact that OS bisects chord QP, OS will be perpendicular to QP. If OS perpendicular to PQ, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to all 30. Again, because of the fact that OS bisects chord PQ, OS will be perpendicular to PQ. That is to say, this angle equals to 90 degrees and this angle also equals to 90 degrees. Okay, so in the next step, we define the length of SO is Y, the length of ST is H. We know that OD equals to 1 half, so we implemented the Pythagoras theorem on this triangle, right triangle SOT. So I copy the right triangle SOT in the new page and we implemented on it the Pythagoras theorem. This is the right triangle SOT, that I copy from the original drawing. This right triangle SOT, SO squared, that is the square they hypotenuse, equals to ST squared plus OT squared. SO is Y, therefore SO squared is Y squared, it is equals to ST squared. ST is H, therefore ST squared is H squared, plus OT squared. OT is 1 half, therefore OT squared is 1 half squared, that is 1 quarter. So in total, according to equation 1, we can find out that Y squared equals to H squared plus 1 quarter. Again, Y squared equals to H squared plus 1 quarter. In the next step, we join points S and N together by a straight line. Point S is the center of this small semicircle. Point N is the point on the small semicircle itself. Therefore, Sn is the radius of this small semicircle that is equals to X. So in the next step, I copy the right triangle STN and in page and we implemented on it the Pythagoras theorem. This is the right triangle STN that I copied from the original drawing. Tn equals to 1.5 units in its length. This right triangle STN, according to the Pythagoras theorem, Sn squared, that is the square of the hypotenuse, equals to St squared plus Tn squared. Sn is x, therefore Sn squared is x squared, and it is equals to St squared. St is h, therefore St squared is h squared, plus Tn squared. Tn is 3 quarters, 3 halves, and therefore Tn squared is 3 half squares, that is 9 quarters. In total, according to equation 2, we found out that x squared equals to h squared plus 9 quarters. And again, if we found out that according to equation 2, x squared equals to h squared plus 9 quarters. This is according to equation 2, and according to equation 1, we only found out that y equals to h squared plus 1 quarter. In the next step, we subtract those two equations, so it is 2 minus 1. 2 minus 1 means that x squared minus y squared equals to h squared plus 9 quarters minus h squared plus 1 quarter. So in total, x squared minus y squared equals to, open the brackets here, h squared plus 9 quarters, open the brackets here, and it will be, after you open the brackets, it will be equal to minus h squared minus 1 quarter. So here we have in total x squared minus y squared equals to h squared minus h squared is 0, And 9 quarters plus 1 quarter is 8 quarters. 8 quarters is 2. So in total, according to equation 3, option found out that x squared minus y squared equals to 2. This is according to equation 3. So in the next step, we join points P and O together by straight line. Point O is the center of this big semicircle, point P is the point on the big semicircle itself, so 4PO is the radius of this big semicircle, this was 2, 4. In the next step, I copy the right triangle PSO in the new page and we implement the Quadrat's theorem on this right triangle PSO. This is right triangle PSO, this is according to the original drawing. This right triangle PSO according to the Quadrat's theorem, P all squared, this is the square of the hypotenuse, equals to PS squared plus S squared, all square. PO is 4, so 4PO squared is 4 squared, this is 16, and this is equal to PS squared. PS is x, therefore PS squared is x squared, plus SO squared. SO is y, therefore SO squared is y squared. So in total, according to equation 4, we should find out that 16 equals to x squared plus y squared, or x squared plus y squared equals to 16. This is according to equation 4, while according to equation 3, we only found out that x squared minus y squared equals to 2. So we did equation 4 to equation 3. And we found out that x squared plus x squared is 2x squared, y squared minus y squared is 0, and 16 plus 2 is 18. So in total we found out that according to equation 5, 2x squared equals to 18. Here we divided this equation 5 by 2, and finally found out that 2x squared over 2 is x squared equals to 18 over 2, that is 9. So in total we found out that x squared equals to 9. Now just to find out the size of this shaded region. We are talking about this the area of this small semicircle. We know that the radius of this small semicircle is x, and therefore the area of the small semicircle is actually the shaded area. It is equals to pi x over 2. So the shaded area is only equals to pi x over 2. But we just now found out that x equals to 9. So we substitute x by 9 and found out that the shaded area in total equals to 9 pi over 2. 9 over 2 is 4.5, so in total this expression equals to 4.5 pi. So in total we found out that the size of this shaded area, in total it is equals to either 4.5 pi square units in size, or in terms of numbers, the size of this shaded area is equal to 14.137 square units in size. Okay, thank you very much.